In the previous video, we introduced the concept of the atomic composition of all matter in the physical universe, the classification of atoms into elements based on their number of protons, and the periodic table. Atoms, we remember, are the tiny particles that compose all matter, and depending on their number of protons, they are classified as belonging to one of 118 elements. Elements are seen as chemically unique, in that atoms belonging to one element will have chemical properties that make them unique from atoms of other elements. Finally, the periodic table was introduced as a visual representation of all the known chemical elements. In today's video, we begin our discussion of the next foundational concept in chemistry, molecules. To do this, we need to establish some background knowledge, and for that, we have to return to the periodic table and take a closer look at it. More specifically, we have to think a little bit deeper as to how the periodic table itself is organized. Dmitri Mendeleev and the chemists who came after didn't place elements on the periodic table all willy-nilly. The periodic table is actually the product of meticulous study of the properties of the elements themselves, as well as the patterns that appear when they are compared side by side. Now, here we have a really excellent periodic table, taken from this website here, the National Center for Biotechnology Information, abbreviated NCBI, and this is the PubChem periodic table. PubChem is essentially an openly sourced database and information center operated by the US federal government, or more specifically, by the National Institutes of Health. It contains lots of useful information about chemicals and the way they respond to bioassays, which are laboratory tests used widely in medicine and biotechnology research for diagnosis and chemical identification purposes. The reason it's referred to as an openly sourced database is because anyone with scientific data to contribute can add to the already existing information on the site. This means that PubChem is constantly being updated with new information about both newly discovered and already known chemical substances. There's plenty of useful information on there about the chemical elements, compounds, medications, and a lot more. It is highly recommended to check out the website and read through some of the new research being done, because it truly is a brilliant resource. This periodic table specifically is found on a web page, which is listed here, and this web page includes a fully interactive periodic table to click through and explore. It wasn't explicitly stated on the web page whether this representation in particular is in the public domain or not, so the corresponding citation is appended here just in case. Anyhow, if we take a closer look at this periodic table, it'll be immediately noticed that there are these little numbers running on top of and on the sides of the table itself. As stated earlier, the periodic table is not a random arrangement of elements. There's a definite order and method to its presentation. We will explore this more in the next video, but for now, let's explore exactly what these little numbers represent. The periodic table divides elements into two types of classifications, groups and periods. Groups are the vertical columns, while periods are the horizontal rows. In other words, groups run up and down, while periods run from left to right. The purpose of both groups and periods is to classify elements based on shared properties. There are 18 groups found on the periodic table, and that's what these numbers running along the top of the table represent. The number 1 here on the top left-hand side represents group 1, the number 2 next to it represents group 2, and so on and so forth. But how exactly do chemists decide which elements belong in which group and period? All the elements in the same group will share similar chemical characteristics. This similarity arises from the number of electrons found in their atom's outermost electron shells. This deserves a little bit more explanation. If we look down here, we see another drawing of an atom. Like in the previous video, the protons are drawn as white spheres, the neutrons are in blue, and the electrons are in red. It might be noticed that there are exactly 5 protons in the nucleus of this atom, making this an atom of boron. This time, however, we have to focus our attention on these green circles running around the nucleus. These, if it's remembered from last time, are the paths that electrons travel on as they rotate around the nucleus. These paths are called electron shells or electron orbitals. These two terms are synonymous for all intents and purposes. Again, the outermost electron shell, the one this arrow on the right is pointing to, that shell is referred to as the valence electron shell, and the, in this case, 3 electrons orbiting along it are called the valence electrons. So we can say that every boron atom in the universe has exactly 2 electron shells and 3 electrons in its outermost shell, or 3 valence electrons. Now if we return to our periodic table, we will see that boron is located in group 13, in the column numbered 13. Boron is found as the topmost square in this column, and if we begin reading downwards, we'll notice that boron, aluminum, gallium, iridium, thallium, and nihonium are the 6 members of group 13. These elements on the bottom 2 rows, the ones with the chemical symbols dy and Cf, these are actually not part of group 13. If we scroll over a bit, we'll note that these 2 rows are actually an extension of group 2, and therefore we can't count them in the same category as boron. Now, having learned that boron has 3 valence electrons, or 3 electrons in its outermost electron shell, we now know that aluminum, gallium, iridium, thallium, and nihonium all will also have 3 valence electrons and will share some chemical characteristics. Of course, elements are not placed solely based on their number of valence electrons, and groups are not the only parameter by which the periodic table is divided. The periodic table is also divided into 7 periods, or rows, and these are denoted by the numbers running up and down on the left-hand side of the image. Elements in the same period are placed where they are because they have the same number of electron shells. This means that all the elements in period 2 that would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. All of these have 2 electron shells. An element located in period 7, radium for instance, will have 7 electron shells. Unlike with the concept of groups, the period number directly corresponds with the parameter it represents. Boron might be in group 13, but boron doesn't have 13 valence electrons, it only has 3. However, because boron is found in period 2, we know that it must have 2 electron shells. It's important to keep this numerical relationship in mind moving forward. We've now arrived at the point where we need to introduce some new terminology. Thus far, we've dealt only in the realm of atoms and elements, but chemistry is so much more than that. It also involves the study of combinations of atoms and elements, and that is where we get the concepts of molecules and compounds. Simply defined, a molecule is any group of 2 or more atoms fused together to make a new chemical substance. As a quick aside, a molecule can contain 2 atoms from the same element fused together. For example, oxygen gas, or O2, is nothing more than 2 oxygen atoms fused together to make a molecule of oxygen, and oxygen gas is considered as being composed of molecules. On the other hand, a compound is a substance composed of atoms from multiple elements fused together in a fixed ratio. We can cross-reference Dalton's atomic theory on this. The 4th point of Dalton's atomic theory states this exact same concept, and we discussed this very briefly in the last video. Ultimately, there are 2 important parts of this definition. Firstly, there's the idea that a compound is made up of atoms belonging to different elements. The implication of this is that a substance like oxygen gas would not be considered a compound because it only contains 2 oxygen atoms, 2 atoms from the same element. Something like table salts, by contrast, is considered a compound because it contains 1 atom of sodium fused to 1 atom of chlorine. This explains why the technical name of table salt is sodium chloride. Secondly, there is the notion that compounds always exist as a fixed ratio of atoms from different elements. Sodium chloride, or NaCl, will always contain 1 atom of sodium and 1 atom of chlorine. If we were to add 3 oxygen atoms to table salt, we would get sodium chlorate, or NaClO3, which is a completely different compound. Table salt can only exist where there is 1 sodium atom fused with 1 chlorine atom. This will never change. In summary, all compounds are molecules, but not all molecules are compounds. This distinction can't be overstated, and in just a little bit, we will be working through an example problem to illustrate this. Before we do that, however, it's crucial to clarify a matter of nomenclature. which is essentially a fancy way of talking about how things are named. In chemistry, basic nomenclature is done using letters and numbers. The letters involved here are the chemical symbols, the element symbols we acquainted ourselves with last time. Each element has a unique 1 or 2 letter symbol assigned to it, and these symbols are the shorthand way of referring to said elements. Besides the element symbols, chemists also make use of numbers, or more specifically, the subscript numbers found on the bottom right-hand corner of the element symbols. Subscripts are used to denote how many atoms of that element are found in a molecule. Sodium chloride, for instance, is represented by combining the element symbol for sodium, or Na, with the element symbol for chlorine, or Cl. Because a single molecule of sodium chloride only contains 1 atom of sodium and 1 atom of chlorine, we don't need any subscripts in this case. Instead, we simply squish these 2 element symbols together and write the abbreviation NaCl to represent sodium chloride, also known as table salt. 2 more quick examples. Oxygen gas is denoted as O sub 2. It is composed of 2 oxygen atoms fused together. Carbon dioxide contains 1 atom of carbon and 2 atoms of oxygen, so we write the capital letter C with no subscript and write the letter O beside it with the subscript 2, thus making CO2. These combinations of symbols and subscripts are called the chemical formulas of these molecules, and we will be seeing them quite often from here on out. As promised, here is our example problem. Example 1. Classify the following substances as compounds, molecules, or elements. Keep in mind that more than one classification may apply to some of these. First, we're looking at carbon, represented by the uppercase letter C. How would we classify this? Please pause the video here if you'd like to take a shot at this one. Carbon would be classified as an element. This is because it is only 1 atom, as denoted by the lack of subscripts and the lack of a second element symbol. What about carbon monoxide, or CO2? Carbon dioxide is both a molecule because it contains more than 1 atom, and a compound because it contains more than 1 element. Next one, sodium chloride. This one has the same answer as part B. Sodium chloride is both a compound and a molecule. What about oxygen? Notice the chemical formula provided here. There are no subscripts, so this type of oxygen is an element, not a molecule. Finally, we have nitrogen, or N2. How would we classify this? N2 is a molecule, but not a compound. 2 nitrogen atoms are involved here, which meets the criterion for a molecule, but there is only 1 element involved, so this is not a compound. Remember, all compounds are molecules, but not all molecules are compounds. It's also important to mention that most of the commonly encountered substances in everyday life, such as oxygen gas, water, etc., these are going to be molecules, not elements. From all that we've learned about molecules so far, a person might start to wonder about this atomic fusing we've been discussing at length thus far. How exactly do atoms fuse to form molecules? The answer to this question is simple in theory, but it can get complicated rather quickly if we dive too deeply too soon. For viewers watching these videos in order to review for an exam, or viewers who already have some knowledge of chemistry, please try and bear with me here, because this is just the beginning of our examination of chemical bonding. As a matter of fact, the next unit is specifically devoted to the study of bonds that can form between atoms. At the moment, we'll look at a vastly simplified description of bonding to help avoid confusion, and as we expand our base of knowledge, we'll get into all the intricate details and explain everything in a more technically accurate fashion. A simplified definition of chemical bonding is the formation of attractive forces between atoms that draw them together to form molecules. These forces can either be strong and difficult to break, or they can be weak and comparatively easy to break. Today's discussion centers around strong bonds. There are three types of strong chemical bonds that can form between atoms: ionic bonds, covalent bonds, and metallic bonds. Ionic bonds and covalent bonds are the two types that will be most frequently encountered in general chemistry, and metallic bonds will unfortunately fall to the wayside as we move forward in this series. At this point, we ought to pause and ask the question, how do atoms decide which of these three types of bonds to form? We can find our answer, as is so often the case in chemistry, by returning to the periodic table. Besides the classification of elements based on groups and periods, the periodic table can also be divided into three categories: metals, nonmetals, and metalloids, which are also referred to as semimetals. It's important to clarify that these are completely unofficial categories, especially concerning the metalloids or semimetals. Speaking broadly, metals are elements which are good conductors of heat and electricity. This means that they allow heat and electricity to pass through them easily and don't offer much resistance in that vein. We can easily demonstrate this by imagining a metal pot filled with boiling water. It doesn't particularly matter which metal the pot is made of: copper, iron, or some mixture of metals like stainless steel, it's all the same. If a person puts their hand on the side of a metal pot filled with boiling water, the heat will easily travel through the metal and onto their skin, causing a burn. This is what we mean when we say metals are good conductors of heat and electricity. Metals also melt at high temperatures, and they have comparatively higher densities. For those who are unfamiliar with the term, density is essentially a measure of how much mass can be squeezed into a certain area. On an atomic level, this implies that in elements with a higher density, their atoms will be more concentrated. A lump of pure iron, for example, will include iron atoms very tightly packed together compared to the atoms in a lump of something like sulfur, which has a lower density. Under the SI system of units, the unit for density is the kilogram per cubic meter, and mathematically speaking, this unit is nothing more than the unit for mass divided by the unit for volume. Nonmetals are elements that have properties more or less diametrically opposed to those of metals. They are poor conductors of heat and electricity, resisting their movement very well. Nonmetals also melt at lower temperatures and have lower densities when compared to metals. Metalloids are an odd group. They can be seen as intermediates between metals and nonmetals in that they share characteristics of both, behaving like metals under certain circumstances and behaving like nonmetals in other circumstances. Metals constitute the majority of known elements, and they are mostly concentrated in groups 1 to 13 on the left side of the periodic table. A few elements of metals are iron, lithium, and elements that most people may not think of as being metals, such as sodium. Metalloids form an almost diagonal line separating the metals from the nonmetals on the periodic table, and they belong to groups 13 to 17. Metalloids are the best example as to why the categorization of elements into metals, nonmetals, and metalloids is an unofficial categorization. And this is because there aren't exactly any official guidelines as to what makes something a metalloid as opposed to a metal or nonmetal. For example, some of the chemistry literature out there classifies the element polonium as a metal, whereas other books and journals classify it as a metalloid. This tripartite classification is therefore not an exact science. Some of the elements most chemists would agree are in fact metalloids include boron, silicon, and arsenic, which we talked about in the previous video. Nonmetals are concentrated in the upper right corner of the periodic table, except for hydrogen, which has its own lonely spot over on the upper left-hand corner. They occur in groups 14 through 18. Nitrogen, fluorine, and neon are examples of nonmetals. Having introduced the concept of metals, metalloids, and nonmetals, we can now answer our question. Generally speaking, the types of elements involved in a molecule determines the nature of the bonds holding them together according to the following pattern. If a metal and a nonmetal form a molecule, the bond between them will be an ionic bond. If a nonmetal and a nonmetal form a molecule, the bond is covalent. If two metals are involved together, the bond is a metallic bond. I do apologize for the minuscule writing here, but in this context, the word nonmetal applies both to true nonmetals and to metalloids. So if two metalloids form a molecule, or if a metalloid and a nonmetal form a molecule, the bond will be a covalent bond. If a metalloid and a metal were to form a bond, the bond would be ionic. What I'm trying to establish here is that for point number 20 only, nonmetal and metalloid are interchangeable in terms of deciding the type of chemical bonding that will occur. Let's close this video with a second example problem. Example 2 says, predict the type of chemical bonds involved in the following molecules. As a tiny side note, it might be a good idea to pull up a periodic table as we work through this. Number 1, hydrogen gas. What bonds are involved in a molecule of hydrogen gas? Feel free to pause the video here if you like and think about it. Hydrogen gas is a molecule, but not a compound, and it involves two hydrogen atoms. Hydrogen, as we stated earlier, is a nonmetal, so a bond between two hydrogen atoms must be a covalent bond. Next, we're looking at bronze, which is an alloy of copper and tin that was widely used in ancient times to make weapons, statues, and all sorts of things. An alloy, remember, is essentially a mixture of two metals. This right here should be a major hint. Copper and tin are both metals, so metallic bonds are what allow for the making of bronze. What about methane? It has a chemical formula of CH4. The formula CH4 tells us that a methane molecule has one carbon atom and four hydrogen atoms. Carbon and hydrogen are both nonmetals according to the periodic table, and so the bond, or in this case bonds, between them have to be covalent. Final question. What type of bond is involved in lithium chloride, or LiCl? Lithium is a metal found in group 1, and chlorine, which has the element symbol Cl, is a nonmetal found in group 17. A metal and a nonmetal bonding together creates an ionic bond. We've covered quite a bit of ground today, and in Unit 1, Video 3, we will be taking an even closer look at the periodic table as we dive into the topic of periodic trends. Thank you for watching.